What's up, guys? It's Mr. Brengle, and today we're going to be going over the Energy Transformation Virtual Lab Report. I'm also going to be going through the data and kind of how you get some of those numbers. So let's jump into it. We're skipping the first part. We're looking at mass and velocity. So the main thing here is that you're kind of pay attention to what's happening as the mass decreases. So remember, we launched Trevor with a spring, and we're changing his mass. We're leaving the spring constant and the compression the same. So when you decrease his mass, it should make sense that when he has less mass, it'll be easier to accelerate him. Okay, so his velocity does increase as we decrease mass. Okay, so when we're looking at this graph here and you see that, you see his mass is increasing along the x-axis. Well, the y-axis velocity is decreasing. This is what we refer to as an inverse relationship. You can see I have an equation on my graph here. You don't need that for curved graphs. So inverse relationship, meaning that they are opposites. They're inversely proportional to one another. So as the mass increases, the velocity decreases. And this is a hyperbola. So we definitely want to make sure that we linearize this, okay? So to linearize a hyperbola, we want to use that equation that explains this relationship, which is y is equal to 1 over x. Okay, that should make sense. As the x-axis increases, okay, which is in the denominator, that would decrease the y-axis, okay? So if this is x and this is y, then this needs to be 1 over x, and this will stay y. So we're just copying velocity, the velocity graph, or side of the column down here. These should all be the same numbers. Okay, so this column and this column are the same. We're not changing the y-axis. However, instead of doing Trevor's mass, we are now doing 1 over the mass, which is in 1 over kilograms. And then we're going to put in an equation here, equals 1 divided by, and then you're going to click on the mass. And we should do 1 divided by all those masses. We'll just drag that down. And that's what you should have there. So it comes out to be a nice straight line here. We've got a 0.99 r squared value right here. This is our equation for the graph. So the slope is 99.3 times x plus the y-intercept of 1.92. Okay, and that's because we didn't start at 0, 0. But so there's our linear graph. I obviously had mine kind of already pre-made to save time, but you'll want to make sure that your title's correct, y versus x. Make sure you get your units in parentheses here. Make sure it says 1 over mass in the title and on the x-axis, and not just mass. And then 1 over kilograms. Okay, so kind of looking at this lab report here, explain the relationship between the two variables. What happens to Trevor's velocity as his mass increases? Well, we already talked about that, right? As his mass increases, it becomes harder to accelerate him, and he therefore will have a lower speed at higher masses. So this question is worded kind of the opposite of the way that we have it in the lab. We actually decrease the mass here, so just be careful about that. As the mass increases, the velocity decreases. You'll put your linearized graph right here, and then it says, what does the slope of your graph represent? Think about what the units for slope would be. And it says then to do a Google search of the slope units. So let's kind of think about this here for a second. If we did rise over run, so I'm just going to put it in right here. I'm going to put rise over run right here. So what's on our rise? Well, that's velocity. Okay, and then 1 over mass. So we have velocity here, and then that's over 1 over mass. So if we want to get something out of the denominator here, we want to get mass. So think of this like a fraction, right? Okay, so it's, in fact, let me put a little, I'll do this. Okay, so it's velocity over 1 over mass. Well, we need to multiply by the reciprocal of 1 over mass, which is just mass, right? So if we multiply by mass on the top and the bottom, then we're going to get rid of that. We're going to get rid of this. So this will cancel out here, okay, and with this. And then we just have velocity times mass on top. So our new slope is velocity times mass. Okay. Well, you may or may not know this. You can Google search this and find out what this is, but and it might be helpful to put in the units. So this would be meters per second times kilograms, okay? Or meters times kilograms in parentheses over seconds, which you may see that. Either way, if you type this in, what you are going to find is that this is the momentum of the object, okay? So this slope represents the object's momentum right here. Now that's our next unit. I don't expect you guys to know that. That's just a fun little tidbit for you there, okay? Now, this is important here. Look at the results for elastic and kinetic energy for each trial. What do you notice about them? Why is it like this, okay? So if you look at the instructions, it has the equations here for elastic and kinetic energy. And I may or may not have also included it right above these things. So we want to look at elastic energy first. That is 1/2 times the spring constant times the stretch or the compression of the spring squared. We're only squaring the compression. We're not squaring anything else. Okay, so basically this x squared is in parentheses here. Okay. Now, let's put an equation. The nice thing here is that everything for the spring was held constant. The spring constant's 800, we didn't change that, and the compression is 1 meter, and we didn't change that. And those are your two values right there. So we're literally just going to put in 0.5 times spring constant. Actually, don't click on it. Don't click on it. Just type it in as 800. If you click on it and then you drag these down, it's actually going to start including these values here. So just type 800 since it doesn't change. And then multiply that by 1 squared. And we know that 1 squared is 1, but we're going to go ahead and put in the whole equation. And then we'll just drag this down. So it should be 400 the whole time, right? The elastic energy doesn't change because we had the same spring constant the whole time and the same compression for the spring. We changed mass, which has nothing to do with elastic energy, okay? So ideally, when we calculate these kinetic energies here, these are going to be, ideally equal to 400, but more realistically, they're just going to be close to it. So for kinetic energy, very similar equation. Again, it's the velocity that's squared here, nothing else. It's 1/2 times the mass times velocity squared. So we'll actually put in the whole equation here. So we're going to do 0.5 times, we're going to click on the mass, times, and then in parentheses, we need to do the velocity squared. So we'll click on the velocity, we will square that value, and then double parenthesis ending there, hit enter. 393 is not bad. Let's drag it down and see what the others are. 402, 396. Okay, so these are pretty good. Yeah, right around 400. So so look at your results for elastic kinetic energy for each trial. What do you notice about them? Why is it like this? Well, they're basically equal, right, across this way. Each one of these are just about equal. Well, why is that? Because all the energy from the spring has been transferred into energy of motion for Trevor. As he's shot across the ice, once he's no longer in contact with that spring, he's moving, all that energy has been transferred into kinetic energy. Remember that once he leaves the spring and is no longer accelerating, he is going to travel at a constant velocity across that ice because there's no friction, okay? So that is obviously an important takeaway there, okay? So let's go ahead and go to our second one. In this example, we held the mass of Trevor constant. We also held spring compression constant, but this time we have changed the spring constant. Okay, so we increased spring constant and then left these things the same. Okay, so we're going to do kind of the same thing here, right? I'm going to talk about this graph first of all. So we graphed spring constant and velocity. Spring constant should be on your x, velocity on your y. Honestly, in the title up here, we do not need units. It just makes it a little busy, but you do need them on your x and y axis. You see I've got an equation here and a trend line. This is linear already. We do not need to do any linearization with it, okay? So basically what we're seeing here is that as the spring constant increases, then the velocity is also increasing, okay? So this number is getting larger. Well, that should make sense, right? If you make the spring stiffer, you store more newtons per meter, more force per meter in that spring there, that's what this spring constant is referring to, then it is going to launch Trevor with greater force, okay, which will accelerate him quicker while the spring is in contact with him. And then once he leaves the spring, he will be moving faster once he starts moving at the constant velocity, okay? So make sure you get that graph. You'll paste that in here. That was the explanation of the relationship between them. And then it says, based on what you learned about Hooke's law and energy transformation, explain your answer to number 3. Why did this happen? So if you increase the spring constant and the stretch or the compression of the spring stays the same, remember this equation is, I already have it on there, F equals kx. Well, if you increase k and you leave x the same, what has to happen to the force? Well, the force has to increase, and that's what I was just talking about. Then you look at this equation, F equals ma, and you say, okay, well, if the force increased and the mass stayed the same, then the only other result there is that the acceleration also has to increase. So that'd be kind of how you explain that there, okay? Now let's look at elastic and kinetic energy. We'll do those same calculations again. So we're going to do 0.5 times spring constant. Now this time spring constant changes, so we'll click on it and then multiply that by, in parentheses, the stretch or compression squared. And again, it's 1. We know that 1 squared is 1, but I am just going to go ahead and put it in to be consistent about how we're making that equation there. We'll drag that down. Whoops-a-daisies. Looks like I've done something incorrect. Oh, I see what I did. Okay. So we're just going to put in 1 squared here. See, that's what I was talking about. So I had clicked on B2. Notice how when I dragged that down, it made all these crazy values. That's because it's taking these numbers here. So as I drag it down, it's using this column. So I just need to actually put in the number 1 for the compression to fix that. And then we'll just drag that down. And you can see that the elastic energy here is increasing as we move along, and that should make sense because our spring constant's increasing the whole time, so that should be increasing. Now, once again, we should see kinetic energy values that match these elastic energy values here. So let's go ahead and put this equation in. It's going to be 0.5 times the mass, which is 100. Again, since that's a constant, type that in. And then multiply that by the velocity, which we click on, squared. And just make sure that you have that in parentheses and use we got a parentheses at the front, and then parentheses, and then a double ending parentheses there. 321 versus 325, not bad. So this one was exact. This one's almost exact, almost. So yeah, these are really good. So these came out well. You can see here, once again, we're showing, this is a different test, but we're showing that no matter what, it doesn't matter what we change, these elastic energies are equal to the kinetic energy that Trevor gains, right? So there's all this energy stored in the spring, and Trevor's in contact with the spring. The spring starts moving and accelerating Trevor. All that elastic energy is being transferred into kinetic energy, and then once Trevor leaves the spring, all of that energy has been transferred over to kinetic energy as he starts to move at a constant velocity. So you'll make sure that you get that in here too. And again, this is pretty much the same answer. There's a common theme here, guys. I'm trying to get you, I'm really trying to hammer this into your heads. Energy transformation, right? All the elastic was transferred into kinetic energy for Trevor. So we'll go ahead and move on to our last one here. And in this example, we left Trevor's mass the same. We left the spring constant the same, but then this time we started changing the spring compression, okay? So as you compress the spring further and further, what happens to Trevor's velocity? Well, it is increasing here, okay? And again, we see this on the graph as the spring is compressed further and further. This is in meters here. Then Trevor's velocity that he leaves the spring with is increasing. Again, when he's in contact with the spring and the spring is moving, shooting him forward, he is accelerating. But these velocities in these columns here is the velocity that he leaves the spring with, and then since he's on frictionless ice, he's going to continue at a constant velocity. So once he leaves the spring, Trevor moves at 2.821 meters per second the rest of the time. Then we increase the compression of the spring, his exit velocity increases, and so on and so forth. So you can see I've got an r² value of 1, which is perfect. And then this is our equation right here. So we don't have to do anything to that graph. We'll go ahead and do our elastic and kinetic energy equations. So elastic energy is equal to 0.5 times, we will actually just type in 800 for your spring constant since that number does not change, and then multiply that by the compression, which we will click on this time because it changes, squared. Okay. So, and again, this equation's up here if you need to see it, but I'm gonna go ahead and drag that down, and we could see here that the elastic energy is increasing as the spring is compressed further and further, and that should make sense, right? If you think about, like, for instance, a pinball machine, I don't know if you guys have ever played one of those before, but you pull that plunger back, and what that's doing is compressing a spring. The further you pull it back, the more force that plunger puts on the pinball, right? So all this energy gets stored up in the spring. You compress it further, it's got more energy. Okay, let's go ahead and take a look at what this does to the kinetic energy. So the mass stays the same, so we'll leave that as 100, and then we do need to square our velocities. So we will do that. And we want these to match up with the elastic energies, and you can see that these are once again very, very close. So remember, the reason why they're not exact is because there's a lot of human error when you time Trevor from one blue line to the next in this lab. So as long as they are close, you've done a good job. If they're like really far off, then you probably didn't time it very well. Okay. So, looking at our lab report here, you'll get your graph put in there. What's the relationship between the two variables? We talked about that. As the compression of the spring is increased, so is Trevor's velocity because the spring is now exerting a force on him for a longer period of time. Therefore, he's accelerating for a longer period of time and will be moving faster when he leaves the spring. Why did this happen? We just kind of talked about that, but again, using this equation here, F equals kx, you increase x, you leave k the same. The force that's applied here, the restoration force must increase, and then if you turn that over to F equals ma, once again, that acceleration number, since the mass is held constant, if the force is increasing, then that means the acceleration must increase. And then look at the results for the energies. Why are they like this? Once again, guys, all of the elastic energy is transferred into kinetic energy by the time that Trevor leaves the spring. If there's no friction and everything, then it should be exact. We shouldn't have any loss of energy due to friction or, going into heat energy or thermal energy. Okay. Last thing here, guys, is just the main point, which we've talked about in every single one of these. What happened to all the elastic energy that was stored in the spring? And don't need to go through that. You guys go ahead and answer that. We've been doing that the whole lab. Okay. So if you have any questions, make sure to let me know. But that should get you through your energy transformation virtual lab report.